Okay, hello. This is part B of chapter 12. Well, I'm going to try to finish chapter 12 in this video. So let's get started. I'm going to get rid of my video and start with that section right here. So in the last video, we talked about how to graph. We have a population, right? And I'm going to show you in the next one, which I already set up here. So we have a population, and there are millions of points in the population that we have no idea about. But we assume that there is a correlation between these two variables in the population. And so there is some rho, which is the coefficient or correlation coefficient. And then there is some y that determines all the y values if we know the x values, right? But of course, this is a population of all the points, so we don't have the best model for the points in the population because we don't have all the data points. What do? Take a sample, and then from the sample, we learned in the previous video how to find R and how to find the line of best fit, or the linear regression equation. Now, we call this y hat, which is an estimate for what? For y. We call this A, which is an estimate for alpha, and then B is an estimate for beta, and R is an estimate for rho. All right, now the question is, how do we know that this R is actually that rho? Generally here, we assume that rho is 0. So that would be our, in the hypothesis that we have, to test whether this R is significant or not. It means that whether the R that we found proves that rho is actually this number. Let's say you find R equals to 0.7. How do we know that that proves that the rho is not 0 but is 0.7? Well, we don't know. We have to test it. So one test we do is called the testing of the significance of rho. So we want to test the significance of rho. So in hypothesis, we write the hypothesis this way. Null hypothesis says that rho equals to 0, right? Always. Now you might have somebody claims that rho is greater than or equal to 0. If that's the case, we put it here, but we still, when we do the testing, we only assume that rho equals to 0, right? That greater than in the null hypothesis doesn't change anything. So that's why the researchers don't only put equal sign here. Okay, so the alternative hypothesis could be less than, not equal to, and greater than. For example, if somebody says, I don't know whether rho is positive or negative, but I know it's not 0. So let's say this is the claim, right? So that would be a two-tailed test. So what do? Well, remember the central limit theorem about x bars creating a distribution? So here we have the same situation. We have these R's that every time we take a sample, we're going to find an R, R1, R2, R3, right? These R's make a distribution. And if you standardize these distribution, the R's, you get a distribution that is T distribution. Now, the R's have a standard deviation that is given by this formula, again, from calculus and from other branches of math. We're going to get this and use it here. We're not going to directly find the standard deviation of R's. So, standard deviation of these R's would be this, and the mu of the R's is the same as rho. And since we assume that rho is 0, so the mu of the R's is going to be rho, which is 0 in this case. I mean, in this case of R in this chapter. Okay, now to standardize these R's, we have to take each R and subtract its mu from it and divide by its standard deviation. And if we do that, and we know that rho is always 0, then we get R minus 0, which is R, divided by this, which we can separate into 2 square roots, and then flip it and multiply it by R. So this is a formula for our T, right? And remember, we call this test stat in chapter 9. So that's our test stat for R, for R's. So what we do now, we say the distribution of T's is going to be T distribution, where the degrees of freedom is going to be n minus 2, because we have 2 variables here, so we lose 2 degrees of freedom. So we take this R, we standardize it using this formula, then we take this number just like we did in chapter 9, we take this number, we're going to bring it here either, these are rejection regions, right? So these numbers come from what? Come from T distribution with degrees of freedom of n minus 2, and depending on what alpha is, right? So alpha is the area in the tail here, or the areas in the tails in two tails, and then or this. So depending on what alpha is, we can find out these numbers, and then if this number falls in the rejection region, we reject what? We reject that rho equals to 0. So we're going to support, here. If it's a left-tailed test, we reject that. We say we have evidence to support that rho is what? Negative. And if it's a two-tailed test, and the number falls either in this tail or that tail, then we're going to say we reject that rho is 0. Rho is non-zero. We can't say positive or negative. We just say it's non-zero. That means there is correlation. And if it's a right-tailed test and then T falls here, we're going to say that yes, rho is not 0, and we have evidence that rho is positive, right? That's how we test this R, using T distribution. All right, now there is another way to test this, and that is without using T distribution. And again, that was the time when we didn't have calculators and computers, and working with T distributions was difficult. So instead of, they use rejection regions on T, and also they had another way to do it. So what they did, they said, we're going to set up for just different alphas, let's say 5% and maybe 1% and maybe 10%. We're going to get for different alphas, we're going to find what? We're going to find these R's here, right? For example, what are 2 R's that like 5% they have in the tails, right? And then they created a table for two-tailed test. So if you wanted to test your R, you didn't have to convert it to T. You just take the R, right? Here is your R, and bring it over here and see where it falls, right? So if it falls in the rejection region, you reject. If it falls in the white area, you fail to reject. But the question is, where do you get these R's? And the answer is we have a table for only 5% in this course, in this chapter. In this textbook. Of course, there are tables for other percentages, but we don't really need it. Because if it's not 5%, even if it's 5%, we can use the t-test. And I'm going to show you how to do that. Okay, so there are two ways. Either you convert R to T and use T distribution, or you use R, right? Now, what about so this is the rejection region way to do it. What about p-value? Well, for the p-value, you're going to have an empty what? You're going to have an empty T distribution with T n minus 2. So you take your R, right? You convert it to T, right? And you take your T and see where it falls. If it's a left tail and it falls over here, then you find this area, that's your p-value. If it's a right tail test and it falls, if your t falls over here, then you find this area, that's your p-value. And if it's a two-tailed test and your t falls, let's say over here, then you find this area and multiply it by 2 because you have to take this side as well, right? So depending on where t falls, you can find p-value for it, just like chapter 9. Okay, so that's the big picture. So let's actually let us actually do some examples, okay? And I'm gonna let you read these assumptions that we make when we do this linear regression. I'm gonna let you read that. You can just read it yourself. Stop the, pause the video and read these. There are 5 different assumptions. And then we're going to do actually an example. So testing the significance of rho. The correlation coefficient R tells us about the strength and direction of the linear relationship between x and y. However, the reliability of the linear model also depends on how many observed data points there are in the sample. So it has to do with n as well. For example, if you only have 2 points in the data, well, look, these 2 points fall on a straight line, so R always will be either 1 or what? Or if you have a points this way, R always is -1, no matter what is going on in the population. So you cannot really do this regression analysis with 2 points. You need at least what? You need at least 3 points, right? So you can have a line that goes through them and is closest to all of them. 2 points always is a perfect correlation, right? So we got to start with n equal to 3 actually. With 2 points, you're not going to be able to do that. You can do it, but it doesn't make any sense. So we need to look at both the value of the correlation coefficient R and n. And I talked about that already. I said that we set up the hypothesis to be what? One hypothesis is the null hypothesis that says that population correlation coefficient is not significantly different from 0. That means rho equals to 0. And the other one says not equal to or less than or greater than. Okay, that's the idea. So as I discussed already, there are 2 ways to do that. We can find t, right? We can use R directly, right? But the question is, this can be done only if alpha is 5%, right? We take R and we bring it over here. Now these 2 numbers for 5% come from this table and depends on how many data points we have. So let's say we have 7 data points. Then we go to 7 minus 2 is 5. And for 5 it says what? 0.754. So that would be 0.754, and that would be negative 0.754. Now, if the R that we have falls in the rejection region, we reject. Now, how does it fall in the rejection region? Absolute value of it has to be greater than what? Greater than this R that we get from the table, right? If the absolute value of it, let's say R is 0.8, then absolute value of 0.8 is 0.8 and it falls here. And let's say R is negative 0.8, then absolute value of negative 0.8 is 0.8 and again it falls over here, right? You could also, if it's negative 0.8, you can also put it here and you see it falls in the rejection region. But you don't have to actually draw the rejection region. You don't have to do that to use the table. All you do, you go to the table. See, we got this number right here right? We bring it here. We say, okay, this is our number. If this number, absolute value of it, is bigger than this, then we reject the null hypothesis. That means we reject that rho equals to 0. We know rho is not 0. That's the idea of using R table directly. And this table is in the textbook, and in the notes, if you click on this, you go to that website and you see the table. But they only have it for 5%, so not very useful. But if it's 5%, yes, you can directly do it, so you don't have to convert to T. But if you don't have the table, then you have to get the R from the sample and convert it, right? Remember, T was what? T n minus 2 is going to be R times reciprocal of this, because this is in the denominator is the standard deviation. So it would be n minus 2 over 1 minus r squared. That's our R. That's our T. Then you get this T, and then again, depending on what test you have, you either use rejection region, which we don't have to. We could just do p-value, right? Just let's say it falls over here and is a two-tailed test, and you find this area multiplied by 2. If it falls over here, I'm assuming this is p-value here, right? Not rejection region. Rejection region we don't really need, because rejection region is before technology was available. So this area is p-value, and then if it falls over here, then this area is p-value. And how do we find the p-value? You can do TCDF, CDF, right? TCDF, and then you can put lower and upper, and then degrees of freedom. Depending between two numbers, right? This would be, of course, from negative infinity to that number. This would be from this number to infinity. This would be from negative infinity to infinity. This one you have to multiply by 2, because you have to count this part 2 is a two-tailed test. All right, so let's continue. So let's continue. So here's an example to use R, right? So once the sample correlation coefficient R has been calculated, we need to determine whether there is enough evidence to decide that the population correlation coefficient rho is significant. Significantly different from 0. That's what significant means. That is significantly different from 0. So, and then level of significance has to be given, and that's alpha, right? So here is the example that we did. So remember, this is still in your calculator. So what was R in our example was 0.663. Is this significant? That means, can you say that you have evidence that R rho actually is not 0? So if somebody says rho is 0 in the null hypothesis, do we have evidence against it? And the answer is yes. Why? Because this number is greater than the number that we get from the table. So how many numbers do we have? We have how many pairs? We have 11. 11 minus 2 is 9. So what we have to do, we have to go to the table to 9, row 9, and look at this number right here, 0.602. That means if the absolute value of R that you get from the sample is greater than this number, that means that has fallen into rejection region. That means there is evidence that we can reject the rho equals to 0, right? So what do we say? There is sufficient evidence to conclude that there is a significant linear relationship between the third exam and the final exam scores. Of course, at 5% level of significance, because that table is at 5%, right? All right, so that's directly using R without converting to T. What if we want to convert to T? Well, there is actually, in the calculator, there is a test you can use that it does it for you. Just like chapter 9, we had Z-test, T-test. So here, if you go to stat and tests, you have to go at the end like a linear regression t-test. Linear regression t-test, not interval, but test. Okay, right here. So we pick that one. Now remember that we did linear regression and we found the line and everything, but this actually calculates everything for you. So when you do this test, it calculates everything. So remember we have L1 and L2 are these numbers, right? We still have them there. So I'm going to do now to stat and then go to tests and go to linear regression t-test. And L1 and L2 is good. Frequency I don't have. We have one of each. And let's do a two-tailed test. So that means we assume that H null says rho equals to 0, and H alternative says that rho is not equal to 0. So let's see. Now, if you put y1 here, how do you find y1? Is under variables, y variables, function y1. So what the calculator is going to do, it finds the equation for you and puts it in y1 for you. See? It does everything for you and does the test for you. What else do you want? So let's pick that two-tailed test and y1 and calculate. You see? So what is it? Well, it has the equation, right? See, that's the equation right there. If you go down, you see the rest of it. But it gives you a whole lot more information. First of all, it says what? It says beta not 0 and rho not 0. Why? Because if you say that rho is not 0, rho is related to beta with this formula, sigma y over sigma x. They're related. So if rho is not 0, beta is not 0 either. That's why it says here beta not 0 and rho not 0. Now what is that number? That's the t. If you were to find, remember the r here was like 0.666. If you standardize it and find your t, that t is actually what is that number. And I'm going to show you in the next slide. But it gives you that. And also gives you the p-value already. So not only it calculates t for you, it's going to put it here for you. It's going to put the t here and put the negative t here. Find this area for you. And that's that number right there. So it's about 2.6%. And degrees of freedom is 9. And if you scroll down, you see the equation of the line a and b and r squared, right? And r. And it also gives you another number that is we are interested in a second. In a minute, we're going to get to that. And that is the standard deviation of the errors. We need that later. But for now, it's there. You have to scroll down to see it. Okay, so calculator can easily, with the calculator, it does everything for you. And that you just use the p-value here. And you say at 5% I reject. That's it. And you write the conclusion. All right, so basically by hand, this is what we have to do. We have to find t, which is going to be r times the square root of 11 minus 2, because we had 11 numbers, 11 pairs. And then 1 minus r squared here, and use a calculator, that's what you get. Well, that's the same number that we had. So we don't really have to do this because calculator does it for us. Now, what if you want to do it and you want to find p-value? Well, to find the p-value, you have to take that number and put it over here, right? 2.6576. Find the area to the right of it and multiply it by 2 because this is a two-tailed test. So this is 2.6, this is negative 2.6. And how do you find the p-value? Well, TCDF. multiplied by 2. So 2 times TCDF. Now, this is absolute value of t. That means from t, I put absolute value because absolute value means you use the positive one. So you go from here to there and then multiply it by 2. So you don't have to worry about this part. Right? So whatever t is, you take the absolute value of it, put it here, and then comma 10 to 99, which is infinity, and then degrees of freedom, which is n minus 2. Remember in this chapter, n minus 2, not n minus 1. And you get the same number. See, 0.026, 0.0 is a little bit off, of course, because we did some rounding here, right? If you don't do any rounding and let the calculator use all the decimal places, you get the same answer. All right, so that means that p-value is smaller than alpha, so we reject that null hypothesis right there. So what do we say? We say there is sufficient evidence to conclude that there is a significant linear relationship between the third exam score and the final exam score, right? So that means we know that rho is not 0, basically. All right, now as I said before, calculator says beta and rho not 0 because beta and rho are related, right? Also b and r are related this way. So if rho is not 0, beta is not 0 either. If r is not 0, b is not 0, of course. But that's why it says here that beta and rho not 0. All right, so now the question is, what do we do with this line? Well, we have to predict. How do we predict? We already know how to predict, right? This was just a explanation that we can use the line to predict. Once we know that r that we find is good and the line then is reliable, now we're going to use it to what? To predict the y values for any given x values within the range that we are given. So we go back to the same problem, right? Now in this case, we already found the line. We know r is significant, so we can use it. Now we're going to answer questions like, if somebody makes a, if I know that some students averaged like 76 on the third exam, what should I expect them to average on the final exam? And that's the prediction we're going to make using that line. So here you go. So suppose you want to estimate or predict the mean final exam score of stat students who received 73 on the third exam. So if I want to do that, well, we did this already, right? We found out that it is significant. Now the equation is in y equals 2 already, right? See, the equation is already there. The points are already there and the graph is going through them. So what I like to know is what is the y value for the x value that is 73. So I have to go to 73 here, go up to the line and see what that number is. Well, we can do that in many different ways. I showed you one way already, which is going to home screen, right? And finding y1. So y variables, y function, and then y1. And in parentheses, we put 73, and that's it. So our prediction is 178 is our prediction, right? And that's how we do it. We could have just do it by hand and use 2 decimal places. We get 179 if you do that. But of course, if you use the power of the calculator, then you get this number, right? So we predict that stat students who earn a grade of 73 on the third exam will earn a grade of 179.08 or 178.8 on the final exam on average. So that's prediction. Now, what about 66? Well, we do the same thing. We just put 66 in there, right? And our prediction for somebody who makes 66 is 145, right? That's the idea. Now, what about 90? Well, the data that we have, the data points that we have, let me show you the data points. So data points that we had, well, why don't I go that way? Let me get the calculator. So let's get the calculator and look at the data range that we have. If you go to stat, notice our x values, right? Go from 65, and the biggest is like, what's the biggest? The biggest is like 70 something, 75, right? So the range of the data that we have is like from 65 to some number 70 something, maybe 75. So 90 is over here and is not in the range of the data that we have. If we do that, that's called extrapolation, and I'm going to show you. If you predict for a number within the data points that we have here in this range, that's called interpolation. Interpolation is okay, but extrapolation is risky. For example, here, if you find a value using the model for somebody who made a 90 on the third exam, well, look what happens. What happens is that we get 261, right? Because 90 is not in the range of the numbers that we had for third exam. Remember, that was out of 80, right? So 90 doesn't make sense, and the answer for final doesn't make sense because the final maximum was 200. You can't make it 261 on a test that has 200 points. So extrapolation is not allowed and is risky, but interpolation is okay. So you see, interpolation means, well, we have points, right, like that. But how do we know between these 2 points actually there is the same pattern? We don't know. We don't have data for it. But we say that interpolation is not as risky because it's within the range of the data points. So we assume that between these 2 points, actually the same pattern continues. But if you go way over there, right, well, we have no evidence here to support that this behaves like that, right? So that's not allowed. What is allowed, but is risky. All right. So there is a video for you to watch on linear regression. Now, the last thing we want to talk about is outliers. So what happens is that we have a bunch of points, right? And like in this example, and then we have a line. Some of these points are this far away. Some of these points are, let's say, this far away. Some of them are this far away from the line, right? I should have done it this way. So, so the point is that is there an outlier? Do we have any points that are too far away from the line? And the answer is, well, there might be. So the rule that we're going to use is this. First of all, we know error means what? Means the difference between observed value and the predicted value, right? So that's error. So if this error is bigger, so if E for any point is bigger than 2 standard deviation of the errors. Remember, S was the standard deviation of the errors. If it's more than 2 times that the standard deviation of the errors, then we call that an outlier. That's the idea. So let's do it. So that's the idea I just talked about. So this is far away from the line. This is far away. But how far is too far? So we can call it an outlier. And the answer is, well, as a rough rule of thumb, we can flag any point that is located further than 2 standard deviations above the line or below the line, right? So how do we decide 2 standard deviations above the line? Well, remember in algebra, if we have like y equals to 2x, if I add 3 to it, right, the graph just moves up. Let's say this is 2x. If I add 3 to it, it just moves up 3 units, right? So what I like here is, what I like to have is a line that is 2 standard deviations above this line. We know this line is y hat. So 2 standard deviation above it would be y hat plus 2s. And 2 standard deviations below it would be y hat minus 2s, right? So we're going to get a line like this and a line like this. And we draw those 2 lines, and any point that is within these 2 lines is good. It's not an outlier. But if there is a point that is outside of this range, then it's an outlier. That's how we're going to do this. And we're going to do it for the same example that we just did, the third exam and the final exam. So that's the formula to find the standard deviation of the errors. So we take each of those values, right? And then, so if this is the yi and this is xi, right? So we find this distance right here is yi, and the distance from the line to this is our y hat, I, and this distance here is yi minus yi hat, right? So that's the error. That's what we're going to do. Now, the error, if is, as I just discussed, if it's greater than 2s, then is an outlier. Now, then the point is an outlier. Now, 2s means 2 times s, and where do we get s from? S is calculated this way. So we take all of these distances, and I talked about this before. You take all of these distances, square them, add them, and then divide by n minus 2, not n minus 1, n minus 2, and take a square root. We don't do this by hand. When you do the linear regression t-test, calculator calculates that for you, and is in that list. If you scroll, you see it, s. So we have s. So let's do that. So what we have to do, we have to go to y equals to, where we have the equation for y hat in y1, right? We're going to put 2 more equations in y2 and y3. So you see, we're going to do that. So let's see. And that's s, that's where we get s, right? Let me show you on the calculator. So again, if we run the test, t-test, and everything is set already, calculate, scroll down, that's our s, right? So s is 16.412 something, right? So now we're going to go to, if we want to do it by hand, we're going to have to find what? We're going to have to go to a stat edit, and in L3 go up to the title of L3, and in L3 we can put a formula to find what the difference between yi and y hat I. How do we do that? Well, in order to find this the difference, we have to do what? We have to put parentheses xi here, right? Because how do you find y hat for certain x? So for example, what's y hat for this x, or y hat for this x? Well, remember, we just put what? So in the calculator, in L3, you're going to put, oops, back. So we're going to put y I minus y hat I of xi. Now in the calculator, yi is actually L2, right? Those are the observed values for y, so that's L2 minus, now y hat is in y1, right? And then x values are in L1, so you put L1 in. If you put this formula in here, so I'm going to put what? I'm going to put L2 minus, now I need to go get y1 from y variables here. So y variables, y function y1, and then parentheses, and where are x values in L1? So I put L1 there. I press enter. There. So these are all the differences between yi and y hat I of x, right? Right there. Right? So now we look at these numbers, and we look at 2 times 16 points, because this is s, right? So 2s is what? 2s is going to be 2 times 16.412. Right? What is 2 times 16.212? Well, it's going to be like 32 something, right? Let's say 33. Well, look at this number. This number is what? That number is 34.7. So that difference is bigger than 2s. And that difference belongs to the first point, right? So that means, let me get my calculator back. That means on the graph, this point, the difference between this and what is on the line is bigger than 2 standard deviations. So that point is outlier. Now we could have done it this way. So I put y1 is our equation. So in y2 and y3, I'm going to put, this is the next slide here. Let me erase all this and go to the next slide. I'm going to do exactly the same thing I just talked about. Okay. Oh, that's I did that before. Okay. So here you go. So in y1 I have the equation. So in y2 and y3 I put y1 minus 2s and y1 plus 2s. How do you do that? Well, here you go. So what I do in y2 is I get y1 again from y variables, y1, and then minus 2 times s. Where do I get s from? Well, s is under variables too. So you go to, where is it? Well, under statistics. Where under statistics? Well, let's look for it. Is it under, it's not here. Is it under sigma? Is it under equation? Is it under equation? Well, look below. Is it? No. Is it under test? Is it? Let's see. Is it under test? Yes, it is right there. Right? So S is under test. Remember, it belongs to tests, so it is under test. So we're going to get that S, put it there. And then in Y3, we're going to get, again, we're going to get Y2 this time. I mean Y1, not Y2. And then add to it 2 times S again. We get S again. Statistics, test, and where did S go? It's right there. There. Now when you graph, not only you see that line, right? Not only do you see this line, but you also see what? You also see that line and this line. And notice that all the points are within these two lines, except that one looks like. Sometimes it's hard to eyeball whether the point is on the line or below it or above it. In those cases, just do it numerically, right? Go back. What do I mean by numerically? I mean what? Go to stat and L3 and put the formula in there. So you have all the differences. The one that is bigger than 2S is that one, right? All right. So that's how we find outlier, right? So that's the outlier right there. And so the first point is an outlier. Now, this is an outlier, maybe we made a mistake, right? And numerically, I talked about this already. 2 times S is 32.8, and this is bigger than 32.8, so it's an outlier. Now, the question is, if it's an outlier, why is it an outlier? Did somebody make a mistake? Or is it really an outlier? So what we are going to do, we have to decide on that. You can't just throw it away because it's an outlier. We have to go back to the data and see if somebody made a mistake. If there is a mistake and we are sure, then we can consider that to be a mistake and we're going to delete it. So we delete the first point, 65 and 175. Redo the linear regression based on what is left. Because that number, we were not supposed to use it if it's an error. Of course, you have to prove that. Only if you prove that is an error, you can remove it. All right. So it's possible that some researchers might abuse this idea. And what do? They're going to basically, in order, if they delete it, it favors what they believe, so they delete it in that sense. So they're biased. So that means you have to prove that is an outlier before you remove it. Maybe it belongs there. But it could be an outlier. Maybe that was one student that maybe had a major accident coming to class or something. So it doesn't fit into other, reasons. So you can delete it. So if we delete it, what happens? Well, let's delete it. So we're going to delete the first. How do we delete it? Well, we just go to first point right there. That's the first point. Be careful. Make sure it's the first point when you delete it. And then also you go to L2 and delete it, because right now they don't match, you see. L2 has an extra 1. So you go up to the first one, well, there, and you delete that too. And then you're going to redo your regression. So we're going to go to, in fact, we're going to do the, so what we have to do, we have to get rid of this, because the calculator might give you error because there's something in there and it's trying to put something in there is already filled. So so do the regression, delete that, and then do the test again. So we're going to do the linear regression t-test one more time and calculate. There. And if you go to Y, you see there's a new one, right? And we don't really need this anymore. We can turn it off, but we can have it as well, doesn't matter. So let's go to graph. So that's our new linear regression. And now we don't have outliers, of course. You see, there are no outliers. And notice that what happened to our numbers. R now is what? Let me go to R. Well, they redo it to go to R. Regression theta. Regression t-test. Okay. Well, I have to remove this again in order to do it, redo it. Forgot to do that. All right. So linear regression t-test. That's good. Okay. So look at the numbers. Our R now is what? 0.91. Remember, it was like 0.66. So this is a much better correlation, much stronger. And our data, our line, is actually a much better predictor of the final exam scores if you have third exam scores. So the line changed and then R changed, right? Now we have a better model for this situation. So our new line is that. And then R is 0.91 to 1. Now if you predict, those predictions are better. And notice the R squared is what? 0.83. That means now 83% of the variation in the final exams, final exam scores, is explained by variation in the third exam scores. 83% of it instead of what? 44%. So that's a much better model for this situation. All right. So when we remove that point, R changed. So removing outliers will change the absolute value of R. So when it changes the absolute value of R, it changes absolute value of B. So the line actually changes the slope, right? Depending on how much this changes. So the new line is going to have a different slope, right? So that means, let's say the line was like this, and you remove the outliers, now becomes like that. That's a major difference. And it is caused by the outlier. Now the question is, what kind of outliers do we have? Well, an outlier is a point that is away from the line, right? That's an outlier. And a point that is high leverage is a point that is away from the points, not the line necessarily. So that's a point that has high leverage. Means that x coordinate of it is away from the points on that side or on this side. And the point that is outlier, that means is away from the line and is away from the x values. It's a point that is outlier and high leverage points. These kind of points that are high leverage and outlier are called influential. So they influence R and B strongly. So we have outliers, we have points that are high leverage points, and we have points that are high leverage and outliers. This one has a little high leverage too because it's away on this side. So our point that we had was actually influential point because it changed the slope from, the R from 0.66 to 0.91. All right, So here's an example of application of this. High cholesterol is correlated to what? To heart disease. That means the higher, if these are the points, the higher your cholesterol, the higher risk of heart disease. Okay? So people with high cholesterol have about twice the risk of heart disease as people with lower cholesterol levels. So here is actual graph of LDL and versus what? Relative risk for coronary heart disease. 1 means it doesn't, the cholesterol doesn't add any risk to have heart disease, 1. And if it's higher than 1, then risk goes up. So you see, if your cholesterol LDL level, not total cholesterol, but LDL, is 40, there is no risk. Anything above 40 is risky. See, the higher, the riskier. All right. Now, as I said at the beginning of this chapter, we do y hat equals to a plus bx, so we have only one x. But multiple regression is when we have one dependent and then we have many what? Many variables, maybe x1 plus maybe c times x2 and so forth. We can have more than 2. This is multiple regression. So if we have multiple regression, then to predict, we have to have what? The values for all the variables. As I said, we are not going to discuss how to find equations with multiple variables. In fact, calculator doesn't do that. We need computer. And this is for more advanced stat courses you can take. Or you can read it yourself. You don't have to take a course. You can read it yourself. Okay, so multi-variable regression deals with that. So here is an example. In which of the following situation can multiple regression be performed? Select all that apply. Is that multiple regression? Predicting the number of occupant of a building given its height and the area of the ground floor. So number of the occupant is maybe some number plus what? Some number times x1 plus some number times x2. So x1 is the height of the building and x2 is the area of the floor of the building. And the height is x1. Yes, because that's multiple regression, right? So A is good. Predicting the starting salary for a recent college graduate given the graduate's grade point average. No. That's the salary equals to some number plus and then 1x only, and that's the grade point average. That's not multiple regression. That's the regression we just talked about. So B is not. What about predicting the shoe size of an adult male given his hat size and weight? Yes. So the shoe size maybe can be predicted by, x1 is the hat size and x2 is what? The weight. So if we have the hat size and the weight of the person, we can predict what? The shoe size. So that's good. A is good, C is good. Predicting the average daily commute time in minutes given the distance between their homes and their workplace. No, because that would be just single, right? The distance is just one variable. So A and C, the answer for this. Example, an educational consultant wants to predict the annual salary of teachers in a school district in thousands of dollars, given the number of years of experience teaching, which is x1, and the number of years of education, which is x2. So we have a model for that. Someone's salary, the teacher's salary, is given, predicted by this equation. So y hat is the teacher's salary. This is how many years of experience, and this is how many years of education. Predict the annual salary of a teacher in thousands of dollars with 6 years of experience and 20 years of education. Round to 3 decimal places. So all we have to do is use a calculator and just put this plus this times the number that we are given, which is 6, plus this times 20 years of education. So 53,537, because it is in thousands, right? So we have to move the decimal 3 places to the right. These are in the y hat is in thousands. So the number that we get, we have to multiply it by 1,000. And that's it. All right, so we're gonna end this video here. And again, I'm gonna say bye until we meet next time in next chapter. So this is the end of chapter 12. So take care of yourself and others. See you in the next video.